So this is G485 homework booklet question 10, and starting off simply being asked to define the magnetic flux, and that's the flux density multiplied by the area perpendicular to the flux. We've now got a generator coil. We're going to be coming back to this diagram a lot. A generator coil, 500 turns, a cross-sectional area 2.5 times 10 to the minus 3 meters squared in that magnetic field of that flux density. The plane of the coil is perpendicular to the field, so we've got the field coming in and out of the paper here, and as it's drawn the coil is flat on the paper. Calculate the magnetic flux linkage for the coil in that position, give a unit for your answers. So we simply need the flux, which we've got the flux density in the area, so BA multiplied by the number of turns, so it's NBA, it's the basketball equation, and that gives us 500 turns, 0.35 for the density multiplied by that area, and that gives us a flux linkage of 0.044, and the units of linkage, as indeed the units of flux, are Weber, WB. Moving on, we've got the coil being rotated, shown in the direction shown on that diagram, and we get a graph as a result showing the variation of the flux against time as the coil is rotated. Notice this is flux, not flux linkage, and we're getting a cos curve. So we start up at the high value, we go to 0, goes low, goes and so on, but cos curve. And the next question asks us to explain why the magnitude of the magnetic flux through the coil varies as it rotates. So why does it change? And there's kind of 2 marks here, and possibly if you explain that well enough that would get you the whole lot. But the starting point is that the component of B that is perpendicular to the area changes. So as I rotate that coil round, the component of the field that is perpendicular to that area changes, and then really to take that further you need to explain it in terms of BA cos theta, explaining the shape. You could also do that in terms of explaining that when we're at 0 degrees we're going to be at a maximum, as shown in the diagram. If once that had rotated 90 degrees, we'd be looking at the edge there, so there'd be no flux passing through the coil. Once we go to 180 degrees, it would be at a maximum magnitude again, and then 270 degrees, it would be 0 again, and so on. So we've got that, we've explained why that. So we're now asked to state Faraday's law of electromagnetic induction, that the induced EMF is the rate of change of flux linkage. Now I've got to use that previous diagram to describe and explain the variation in time with the induced EMF across. The explain bit is really very straightforward. Because EMF is rate of change of flux linkage, and you've given that in the previous answer, you can't really quite give that, but what we can do is say that the EMF is going to be proportional to, I've written here is, but it's going to be proportional to the gradient. The gradient is the rate of change of flux, and we're looking for rate of change of flux linkage, so there's that factor of 500 for the turns. The describe part, the EMF is going to be maximum when the flux is at 0, and the EMF is going to be 0 when the flux is at a maximum. Let's go back to the diagram and have a look at that. So the induced EMF is going to be proportional to the gradient. So the gradient at these points, at these maxima, is 0. So the induced EMF is going to be 0. So the induced EMF will be 0 when the flux is at a maximum. You could give that in terms of the actual times, and the EMF is going to be maximum where the gradient is maximum, which is at the points where the value of the flux is 0, those points there. So yeah, that gives those ideas. There's some other things you could say. You could point out in the description, for example, that the EMF and the flux have got the same frequency. If you're feeling really clever, you can point out that there was a phase difference, but I think the 3 easy marks are those first 3 I've given. The EMF is maximum when the flux is 0, and the EMF will be 0 when the flux is maximum, because the EMF is proportional to the gradient of the graph. It then asks us to use that diagram to determine the magnitude of the average induced EMF for the coil. So the EMF is, if we're being asked about the average, it's going to be the change in flux linkage in that time period divided by the time, and we're simply going, the time that we're being asked about is the time until here, so it starts off at that value and goes to 0, so the change in flux is 8, and we've got to look at that. We're just over, well, we're 2/5 of the way between 8 and 10, which is 8.8 for this value here. So 8.8 times 10 to the minus 5 is the starting value. The ending value is 0, so that the 8.8 times 10 to the minus 5 becomes the change in flux. We need flux linkage, so just whizzing back to where I've written the answer. So there's the change in flux, multiply it by 500, it becomes the change in flux linkage, and divide it by the time interval to get the rate of change of flux linkage, which is the induced EMF, and it works out as 8.75. Really neat question next. State and explain the effect of the magnitude of the maximum EMF across the ends of the coil when the coil is rotated at twice the frequency. Now if we come back to, again, if we go back to the graph, I've also seen this question asked about asking you to sketch for an EMF against time graph the changes, because there are two changes. If I'm taking this to twice the frequency, then what I essentially do is to squash that graph down. Oh look, I can have to, so that would all squash in that direction, and I'd be getting the same changes of flux linkage in half the time, so that would be doubling my induced EMF. So going back to the question, the maximum EMF is going to be doubled, okay, is the state, and the explain, because the rate of change of flux linkage is doubled. That's G485 homework booklet question 10.